Hi all, and welcome to the Medical AI Lab group session. Today I'm delighted that we have Shreya Johri from the lab presenting on Auto-Encoding Knowledge Graph for Unsupervised Medical Report Generation. So without further ado, Shreya, take it away.
Hi everyone, today I'll be talking about this paper, Auto-Encoding Knowledge Graphs for Unsupervised Medical Report Generation. And I'd like to begin with a little bit of background about graphs. So graphs are very useful for representing unstructured data sets, and they usually consist of nodes, which represent the graph entity, and edges that represent relationships between different nodes. So depending on the kind of relationship, these edges could be both directed or undirected. And it is important to note that in the formulation of like this, in this formulation, the graph is usually not as useful to us. So we want to make sure that we have some low dimensional representation of every node so that we can then try to analyze relationships between different nodes more effectively. So usually how this is done is that you have some kind of a encoder network, which takes this node and then tries to embed it in a latent space. And this is done in a fashion such that the similarity and relationships between different nodes is maintained in the latent space as well. So it involves a step of parameter optimization and a definition of a node similarity function, which is similar to a loss function. And so this paper talks about medical report generation. So I thought it might be also useful to go over this. So medical report is basically a long paragraph text, which describes both normal and abnormal findings in a given medical image. And one of the reasons why there is interest in trying to automate this process is because writing medical reports is very time consuming and tedious. And if we are able to automate this process, we can reduce the burden on clinicians as well as help in clinical decision making. So currently, what happens with the models that exist before this paper, these models were using supervised approaches. So basically, they were relying on paired image and text reports. So for the same image, you have a corresponding report. And there are a few problems with this approach. So like paired medical data is difficult to acquire, as we can also see from some of the examples that I have here. So Mimic CXR and IU X-ray are two medical data sets. Both have chest X-ray images and reports. And we can see that the size of these data sets is much more less as compared to the size of ImageNet or conceptual captions, which are non-medical data sets. Also, medical data sets can only be labeled by professionals. And so getting these data sets is also, again, more difficult because it's labor intensive, it's very expensive to do it. And there are also patient privacy related concerns, which is why a lot of the times these data sets are not made publicly available. And just to also briefly talk about some more related work in the field. So medical report generation has been around for a while. This paper was not the first one to talk about it. Most of the models that use this are encoder and decoder based models. So the encoder is basically encoding the image, and the decoder is then taking the encoded image and then generating a report. And all of these models, in most of these models, like transformers and hierarchical LSTMs, were preferred decoders of choice. For the knowledge graphs, so knowledge graph, just to take a pause and define what knowledge graph is. So knowledge graph here means that it's a graph, just like I showed before, and it's representative. It's made from a huge corpus of data. So that's why it is in somehow encapsulating all the knowledge in the form of a graph, and hence it's called a knowledge graph. So in this case, the graph has been made from a medical data set. So it's called knowledge graph. So this concept of knowledge graphs in medical report generation has also been used previously, but it has been used in a supervised setting. So in the case where you have paired texts and images, in the past, like people have also tried to use it to boost performance of these supervised methods, because you're then providing some kind of supervision already before you train the model itself. So that's also proven to be beneficial. So what the paper did was, and I'll go over the model in more detail, but just very briefly, this paper is the first attempt to do unsupervised medical report generation, where you have a separate corpus of images and a separate corpus of text, and they are not in any way paired. And then you're trying to see if you can still do meaningful report generation. And they have some different experiments which I will just go over in a while. But so let's start with the model itself. So the first thing that we need for the model is to construct the knowledge graph. So for constructing the knowledge graph, they are using reports from publicly available chest X-ray datasets. In this case, the nodes are basically the most frequent abnormalities and normalities that occur. The edges are they're calculated by some form of normalization on the co-occurrence of different nodes. And once you have this graph, then you want to again embed it so that we can then make sense of all this data. So to do this, they use a very simple approach. So it's formulated mathematically like this, but what it's essentially doing is that it's taking a node VI, and it's looking at the neighbors of the neighbors of this particular node. And then these neighbors are multiplied by the edge weight, and there's some trainable weight matrix, and then they're just doing some kind of ReLU. So this is like a process which can help in generating this graph. So they do this graph generation at the first step of the process. Once you have the graph, now you come to the images and the reports. So the idea is that you want to utilize, so there is a knowledge-driven encoder. So the idea is you want to utilize this knowledge graph so that you can extract knowledge representations from these images and these text reports. So the images, in this case, the image I is passed through a ResNet 50 encoder, which has been fine-tuned on CheckSpurt, which is another chest X-ray dataset. This gives us image embeddings, and similarly, the report R is passed through a transformer model, which will give us the text embeddings. So once you have these image and text embeddings, what do we do next? So these image and text embeddings have not yet been contextualized in terms of the knowledge that we had from the knowledge graph. So now what we want to do is that we want to use some kind of mechanism such that we can relate it back. So in this case, the authors are using attention mechanism. So there is attention, they calculate attention between the image embedding that was just calculated in the previous step, and they calculate attention with respect to this V dash. V dash is the graph embedding. So we had the graph, then we embedded it, and then we are looking at this embedding in the latent space with respect to the embedded image. And similarly, we do the same for the report. After these attention values are calculated, you pass it through this function f. So what is f? F is a simply there are two fully connected layers with a ReLU in between. And so it's interesting to know that there are two separate encoders for the image and the report, but they have some common shared, they are in like some common shared latent space because of two reasons. So one is that you're having some the attention mechanism with respect to this knowledge graph. And second, you have this common function, this common f, which is basically, it has the same parameters. So it's converging in some sense and making sure that these knowledge representations, which we are denoting by GI and GR, are in a shared latent space. So once we have this, then we have knowledge representations. Now we want to decode this so that we can generate the actual report. So in this case, since we want to generate a long report, the authors are using a 3-layer transformer as a decoder, and they have incorporated knowledge-driven attention, which I'll talk about in a second. So the idea is that so they mathematically define the knowledge attention, knowledge driven attention as a attention calculation between HT, which is, so in this case, XT is a word, and it is the word embedding plus the position embedding combined. And you are calculating attention first of this word with respect to the others, which is similar to how you would do in a sentence. And then you use this, and then you calculate its attention with respect to, depending on whether you are doing training or inference, you would use report, GR, which stands for the report, the knowledge representation of the report, or GI, which stands for the knowledge representation of the image. And after that, this basically helps in decoding this knowledge representation that you had in the previous step. So coming to model training and inference, so how does this work? So first we have just going over the training data sets and the inference data sets we used. So Checkspert is used for the images. Mimic CXR, the train part of it is used, but only the reports from this is used. The images are discarded because we want to do unsupervised training. And similarly for IU X-ray also, only the train is used. The test is discarded. And Mimic CXR and IU X-ray have previously labeled examples that fall into the test and the train category. So that's how they divided this. For the inference, we then use the test versions of Mimic CXR and IU X-ray. So for the encoder, the task is that you have these knowledge representations. They get fed into a common multi-level classification network. So this is a common network because because the F that was present in the encoder is common, and you want to make sure it has the same weight. So you want to make sure that it is GI and GR are fed into the same network. And the loss function is a binary cross entropy loss, which is done for 14 of the radiographic observations. And these radiographic observations are actually also present in Checkspert. So that's how this is done. For the decoder, since we don't have any labels, the authors used a method in which they basically started with the report, and their final objective is to regenerate the report. So they go from the report to the knowledge representation, and then finally want to get the report back. And the loss function in this case that they're using is cross entropy loss, defined in this way. For the testing on inference, which is basically when you have an image, you put the image into the network, and the network is already trained, and you want to get the report. You want to make sure that this report is actually representative of what the paired report to this image was. So in this case, the authors use multiple evaluation metrics to see if the model is performing well or not. So some of these are NLG metrics, which are very popular, like BLU, Meteor, Rouge are, and also they used a metric for clinical efficacy, which was helping to make sure that the report is also making meaningful detections of abnormalities in the image. So coming to some of the results for this paper. So the authors then evaluated the unsupervised performance of this KGAE model with other models, that state-of-the-art models or other previous models that exist based on NLG metrics. And in this case, I would like to draw your attention to the red boxed numbers. So basically KGAE in this case is performing better on all the metrics. So B1 to B4 are BLU metrics, and this is Meteor and this is Rouge L, and it's performing better than the top 3 models on all the metrics, and also performing better than the transformer for 3 of these metrics. It's not able to perform better than the other more recent models though. When we look at the clinical efficacy for the same models and the models that has been proposed, we see that again it performs better than the M2 trans, but it's not able to perform better than the other models. So just to also define what clinical efficacy method that they used, so they took Chexpert to label the generated reports to label whether the report has which of the abnormalities are present in the report. And then they compared, and these had like basically 14 different categories which are there in Chexpert. And then they try to see if the report that you generate also has that or not. That's the clinical efficacy that they try to use. Then the authors try to see, so in the previous case, it was all unsupervised. So now the authors are saying that what if we put some supervision into the model and then see what happens? Like, so what they do is they take the unsupervised KGAE and they fine tune it after it has been already trained with some image text pairs to yield a semi-supervised model. So in this case, and they also want to make sure that it is at the same level for comparison. So they retrain the R2 gen, which they are comparing to in this case, with the same amount of image text pairs. So what is observed is that the semi-supervised model is, so in this case, you can see like the red bars are corresponding to the KGAE. It is performing better than the blue bars, which is the other model, which is, and in all the cases, it's performing better, no matter how much training data, like how much supervision you added. And it's interesting to know that if you had less number of pairs, the difference was more stark between the performance of these two models. They also wanted to do some human evaluations. So because it's also very important to make sure that clinicians are finding this model actually beneficial in the clinical practice. So they invited 3 clinicians to quantify the effectiveness. They found that for the unsupervised KGE, which is in the first 2 sort of columns, it is performing better than M2 trans, but it's not able to beat the R2 gen in terms of clinical efficacy. But in other cases, like when it's trained, when it's a semi-supervised model or a fully supervised model. So fully supervised means it's 100%. After it was unsupervised, they trained it with a full data set of image text pairs. So in both these cases, it's able to perform much better than the state-of-the-art model. So this was nice. The authors also wanted to make sure, so this is just a sanity check kind of a experiment, but they also wanted to make sure that the model is not sensitive to the knowledge graph that they had initially made. So in this case, they generated multiple knowledge graphs with different combinations of the chest X-ray data sets that they had, and they showed that no matter whichever knowledge graph you have, the performance is, the model is beating performance for these 3 models and the transformer, which was also the case with the original result that they had. So the conclusion is that it's not sensitive to knowledge graphs. They also did like ablation studies to make sure, just to get a sense of what the model is doing and what part of the model is important where. So for the so F in this case is part of the encoder, B is part of the decoder, which is the knowledge bank. So in the unsupervised setting, they see that despite variations in B and F, it's not like changing the performance much. It's kind of similar. But when you see in the unsupervised setting, so for example, if we compare E and F, we see that the F, when you add F, the performance is unchanged. So it says that the supervised model is, it kind of says that once you have the supervised model, you don't need to bridge maybe you don't need to bridge the vision and text latent spaces, which F was basically doing. For the H and G, they see some different, some unexpected results, but so it's performing better for mimic CXR, but it's not performing better for IU X-ray, which the authors then speculate could be because mimic CXR is much, much bigger and hence has much more knowledge, and hence that's why it's able to boost performance. And then finally, they do some quantitative analysis just to look at the actual report, like what the report is that is generated. So purple is basically bad. It's the generated wrong sentence. Blue is good because it's capturing the true abnormalities, and underlying text is a repeated sentence. So they basically just see that the original unsupervised KGAE was not generating, like at least in this example that's shown, is not generating, and there's no purple, so it's not generating wrong sentences, and it's generating able to find some true abnormalities, which is good. And they do some comparisons in the semi-supervised and supervised setting, which also indicate to sort of the superiority of the KGAE method. So in the end, there are some, they also point out some limitations and potential for future work. So they say that this method does require independent sets of medical images and medical reports, which may again be difficult to collect in large proportion for different kinds of images, which is a potential limitation. And also an application to a new image kind, for example, MRI, retinal images, would require reconstruction of the knowledge graph itself. But overall, the study did show good results. And that's all I had. Thank you.
Awesome. Thanks for the fantastic presentation.